Today we look at phase plane analysis and how the type and sign of a system's eigenvalues classify the equilibrium point at the origin. An equilibrium point at the origin can be a node, a saddle, a spiral, or a center, depending on those eigenvalues. Let's classify the origin for a system whose matrix has rows 0, 1, and -4, 0. To find the eigenvalues, we form the characteristic equation from this matrix. Working through the characteristic equation, we get eigenvalues equal to +2i and -2i. Both eigenvalues are purely imaginary with no real part at all. Purely imaginary eigenvalues mean the origin is a center. A center means the trajectories are bounded, closed elliptical orbits that neither spiral inward nor spiral outward over time. So this equilibrium is neither stable in the sense of attracting nearby points, nor unstable in the sense of repelling them. It simply loops forever. Now let's check this by solving the equivalent second-order equation directly instead of using the matrix eigenvalues. Rewriting the system as one second-order equation in a single variable and solving it gives a solution that is a combination of sine and cosine terms with a fixed frequency. This confirms the trajectory traces out a fixed ellipse in the phase plane, repeating the same closed loop again and again, rather than spiraling in toward the origin or spiraling out away from it. So our classification is confirmed, the origin is a center.